All right, so welcome back. So we are still in section 1, chapter 11. This is part B of the video. So hopefully so far so good. Again, just kind of some housekeeping. So I do realize that many of you have had access exposure to vectors, and therefore you might be this might be a little bit elementary compared to some of the things that you've done, but I cannot assume prior knowledge of vectors, so we will have to continue to push forward. And just remember that if the videos seem lengthy, just remember that these videos are supposed to take place of 3 hours worth of lecture a week, right? Nevertheless, I think we've got all the housekeeping out of the way. Let's jump back in and continue. So last we saw each other, we were discussing some of the various vector operations, right? The sum, scalar multiples, negatives, differences, etc. What we want to do right now to begin this video is start off just using some of these vector operations for the following two vectors. Okay, so we have vector v, we have vector w defined as follows. All right, and we're going to jump right in. So part A, we are asked to find half of v, right? So, and you could geometrically, you could think of vector v has a length, and we want half of that length. So in this case, we can simply we can substitute vector v in for part A, and we're just simply going to take half of each component, right? So we're going to take half of the x component, we're going to take half of the y component, and the result will be a vector with maintaining the same direction, right? So it's still moving in the same direction, only the magnitude is now cut in half. So let me finish this up. So this would be negative 2 divided by 2, comma, 5, my apologies here, 5 divided by 2. All right, so I'll finish that up. So negative 1 and 5 halves. Okay, so here is your new vector. It's been scaled by a quantity of 1/2. Let's go to part B. So now we want to talk about the difference between these two vectors, right? So it's vector w minus vector v. So we got w minus v. Simple enough. I'm going to go ahead and substitute in. So that's the equivalent of asking, so w is 3, 4, minus v, which is negative 2, 5. And now what I mentioned to you is you're almost better to think about, so I'll change my color here. You're better to think about when discussing differences of vectors. I think it'll be beneficial if you just consider w minus v to be the same as saying w plus negative v. That might be more helpful in thinking about how that we proceed. But once we're here, just imagine that we're going to have to change, because we're subtracting this vector here, we're going to change the signs of vector v, because when the negative version would maintain the same magnitude, it would just be in a different direction. So this is 3/4 plus, we can now think of it as now changing my signs. This would be 2, comma, negative 5. All right, let's go ahead and finish this up. So To find the sum, we're going to add each component. So this is going to be 3 plus 2, right? So we're combining our horizontal components, and let's also combine our vertical components. So that would be 4 minus 5. All right, the result is the vector 5, and that would be -1. All right, last one. I think what I'll do is I'll kind of just give you the answer for part C. You can, on your own time, you can go through and make sure that you can produce the same answer that I'm producing, but the answer to part C is 413. All right, let's keep going here. So the following theorem, 11.1, we've already discussed some operations of vectors, right? So how do I add vectors? How do I subtract them? How do I scale them? Notice that we have not discussed how to multiply vectors yet, right? So we will get to that soon. But now we also need to know what properties are upheld during these operations, right? So in mathematics, that we take certain things for example, right? So we take things, for example, like u plus v is equal to v plus u, or v times u is equal to u times v. Now, but when you're creating a system, right, where you need to establish, you need to prove each of these properties. And what you'll find is there are certain systems. For example, if you know anything about matrices, right? If you take a matrix A times a matrix B, that is not necessarily equal to matrix B times matrix A. In fact, that is, I would argue, is highly unlikely that that you could reverse the order like that and still get the same product. So but on your own time, you can kind of run through some of these basic properties. With vector operations, you do have this commutative property of addition, so you can, an associative property, etc., etc. To kind of take you just a little bit farther, all eight of these properties makes up our vector space. So these are what's referred to as vector axioms. But nonetheless, we don't need to go into that in great detail right now. Let's actually just go to the next concept. I'm not skipping them. The proofs of these are fairly trivial, but I think we'll have better use of our time if we just continue. So the next thing, the next bit of theory that we want to discuss is the idea of what we call a unit vector, right? Or normalizing a vector, but in the direction of v. So to make sure you understand what this theorem is saying here. So let me just make up something. Ready? So let's assume that this is our vector. Okay? And now let's assume that you want to preserve the direction of this current vector, but you want a new vector that is moving in the same direction but has a length of 1. So that's what we mean. So a unit vector, a length of 1, but we're preserving the direction, so it's a unit vector that's in the direction of vector v. And now how do we do that? Well, we have to assume a few things, right? We have to assume that this v, vector v that we're interested in, it can't be a zero vector. But if it is a non-zero vector in a plane, then the vector u is going to be the unit vector in the direction of v. So just make sure you understand. So u is going to be in the same direction as v, only it's going to have a length of 1. And how do we do that? How do we get u? Well, it's pretty simple. We're going to take vector v, whatever it is, and we're going to divide it by its magnitude. Simple enough. So let's go to example 4. So in example 4, it says find the unit vector in the direction of v, and v is -2, 5. Let me go ahead and write that a little bit larger. So here's v. This is what we have. All right, now we want a new vector. Okay, this v is not good enough. We want a new vector. We're going to call this new vector u. And what we demand is that u be in the same direction as v, but have a length of 1. And how do we do this? Well, as I stated, the formula, which I'm going to write here, u is going to be vector v divided by the magnitude of vector v. All right, so let's proceed. So let's start with we already know v, but what we don't know is the magnitude of v. So let's go ahead and do that right now. So the magnitude of v. All right, well, as you recall from a previous formula, so the magnitude can be taken by simply using the square root of each of its component of the vector's components squared. So we got -2 squared, and we got to take the sum of these components. So and 5 squared. So what is that? So we got 25, 4, so we end up with the square root of 29. All right. So back to u. So the magnitude is going here, so the square root of 29, and v is going here, -2, 5. Okay. The only thing left to do is this is, although you got the right idea, this is pretty sloppy, right? This is, if someone were to ask you for a vector, you wouldn't see the notation ever written like this. So in other words, we need to be able to go from where we are right now into component form. Let me gonna take this down here. We have the right answer. Let's just go ahead and get it in the right form. Okay, so how do we do that? Well, first thing I would suggest is as you move up into higher maths, you're almost always going to be better off thinking about multiplication by versus division. So in other words, instead of thinking about your age divided by 2, right? I could take your age and divide it by 2. Instead, we can think about that as your age multiplied by 1/2. So to divide by the square root of 29 is simply to multiply by 1 over the square root of 29. Which is exactly what you're seeing here, right? This is the same same notation. And now, again, to finish it, let's just go ahead and go, we can now have a scalar that we're going to distribute to each component. So here is u. It would be -2 over the square root of 29, comma, 5 over the square root of 29. All right. And now, so this is your proposed vector. Let me ask you a question. Let's assume, now if this were a homework question or something, a practice question you were working out of a textbook, there's no real there's no real threat if you were to make a silly mistake, right? There's no stakes involved. But let's assume that this were a test question, a question that, say, you only had 10 questions and you wanted to make sure that you didn't make any silly mistakes. How could you, now to my question, how could you verify that this new vector, u, is indeed a length of 1 as well as the same direction as v? It's a very good question. I will go ahead and that was a two-part question. I'll answer the first the first part of it. So how do we show that this vector, the magnitude of this new vector u, is indeed 1, right? Because that it needs to be a unit vector. Well, it's simple enough. If you want to know the magnitude of a vector, you just use your definition here. So the magnitude of u is going to be, again, now we got the square root of what? Each component. So negative 2 over the square root of 29 squared plus 5 over the square root of 29 squared. And the result of this better get us to 1. So we end up with 4 over 29 plus 25 over 29, which is just the square root of 29 over 29. There we go. So that's, we see it. That's just the square root of 1, which is 1. So we know that this vector definitely has a length of 1. I'm gonna punt on showing you how would you verify that it's in the same direction, because I haven't started to talk to you about angles yet. But you could go through, what you could do is you could verify the slopes, right? That's easy enough. You could take the slope of v, take the slope of u, and that would be one way of verifying that it's still moving in the same direction. Okay, so now my engineers, my scientists, let me get your attention. Wake back up here for a second. So we've been really discussing vectors and just geometric interpretation, right? So now let's get back into the types of vectors that you would have probably been exposed to in your physics classes and engineering classes, and in which you're dealing with what we call IJ or IJK notation. So this is what we refer to as standard unit vectors, right? Now, we're going to start off just in a plane, so we're only going to have an I and a J. But let me go ahead and let me see if I can write what I'm talking about here. So let's assume that I give you the following vector. 1, 5. Now, here's what's important. Here's what's important to really getting the gist of this. So this is one way of writing vector v. Now, let's think about how you would write using this new notation, this standard unit vector, where we're using notation with I and j. Well, the idea is, since the 1, we normally think about that as v sub 1 component, v sub 2 component. Notice something. Notice that the ij notation looks like this. So v sub 1 times I plus v sub 2 times j. But now, what is this I? What is this j? So here's what's important. So these are what we think of as basis vectors. And in other words, how about this? These two vectors, this I and this j, they are actual vectors. Okay? So, but but what's important about them is they are unit vectors, and they are in directions that are important to us. So, let me now define I and J. So here is the definition of I. So notice I is itself a vector, right? But it's a vector, and I'll now show you the geometry here. So it's a vector of length 1, and it's in this horizontal direction, right? J, the definition of J, again, we have a length of 1. And what's interesting is this 1 and this 5 act as scalars. And what are you scaling? Well, you're scaling your unit vectors, basis vectors I and J. So to finish this up, all I'm going to do is substitute the 1 and the 5 in for v sub 1 and v sub 2. So that's going to be, I'm going to write it so that so this is, even though you don't need to have this 1, but just so you know that I have substituted. And if you really wanted to, you could, let me ask it this way. So if I were to ask you to go from component form to this IJ notation, this would be the way that you would do so. So fairly easy, right? Now, what if I were to start you off in this IJ notation and I were to ask you to go to component form? Well, I think you can already spot that it's fairly easy. You're just taking, again, these are linear combinations, right? So you're simply taking the coefficients, and each one of those coefficients acts as a scalar or the component in component form. All right, well, let's actually put some of this to use. Ready? So example 5, I'm going to see if I can make that just a little bit larger. So let me read. So it says, so let U be the vector with the initial point, right, so of 2, -5, and the terminal point of -1, 3. All right, so while I'm going through this, I'm actually going to go ahead and label. So let's label this point P, and let's label this point Q. So in that case, we have U is starting at P and proceeding to Q. All right, let's keep reading. And let V equal 2I minus J. Okay, so in this case, V is equal to 2I minus J. All right. So what is it? What is the task? What is it they want from us? Well, they want us to write each vector as a linear combination of I and J. All right, so let's start with part A. So part A just says simply write U in IJ notation, right? So here's what we have so far. All right, let's get started. So we know U is this directed line segment from P to Q. And notice here's the path that I'm going to take. So I'm going to go to component form, and then from component form, I'm going to go to IJ notation. Okay? So let's get this in component form first, then we'll get it into IJ notation. Well, so this is just a trip from down memory lane, previous video. You recall that to get it in component form, we're going to subtract right? So let's start with Q. So it's going to be -1 x component minus the x component of P. So -2. So this ends up being -1 minus 2. All right, and then for the v sub 2 component, so it's just going to be 3 minus -5. All right, all of this was from the previous video. And let's finish it up. So -3, 8. All right. So if we were asked, if part A asked us to write it in component form, we would be all done. But that's not what we were asked. We were asked what this means, a linear combination. So if you have taken linear algebra, you would remember terminology like this, linear combination. But just remember, what we need to know is it's the sum of these two vectors and scalars, right? So fairly simple to go from component form to ij notation. It's going to be -3i plus 8j. All right, and part A is done. So part B, let's see what we are asked. So we want W, and W is defined to be 2u minus 3v. Okay, so let's actually go ahead and do that really quickly. So let me go ahead and write 2, and then I'm going to insert some parentheses, minus 3, and I'm going to insert some parentheses. And notice that since I already have u in ij notation, I'm just going to drag and drop that here. And I was already given v in ij notation, so I'm going to drag and drop that here. At that point, we're just going to distribute and combine like terms, and we'll be all done. So u would be -3i plus 8j. Sorry. And v would be 2i minus j. All right, I'm going to go ahead and just get us to the answer. At this stage, you would just distribute and then combine like terms. Okay, so distribute and combine like terms. The answer is -12i plus 19j. Okay. Let me just double check that I didn't do any silly arithmetic mistakes. I think we're good. If you see one, you just I don't know, call me out on it. It's all good. Get used to making mistakes, and if you're going to do math. Mathematicians spend the majority of their life being wrong. And the beauty of this science is it doesn't ever forgive you for any mistake you ever make, right? Something special about a discipline that absolutely demands perfection. You have to respect it. Okay, so what we're going to do now is we're going to introduce the idea of the angle, and we can think about the angle between two vectors, because we don't want to continue to talk about slope as our only way of finding direction of a vector, right? Slope is a beautiful concept if you're going to stick to 2 dimensions, but if you want to move into higher dimensions, the idea of slope loses its luster, right? So we want to now start to think about thinking about angles instead of slopes. And now, the way we're going to do this is, let me kind of introduce what I have here. So let's just assume, let's begin with some ifs, right? So if u is a unit vector, right, length of 1, and we're going to assume that theta is the angle that is made, that u makes with respect to the x-axis. And now, what's going to happen here is I'm going to erase this, okay? But normally, if that's u, do you recall? Normally, we think about the component form of u to be u sub 1, u sub 2. Only here in a second, we're going to introduce, instead of, we're going to introduce sine and cosine. So how do we do that? Well, hopefully your trigonometry is fairly up to date, and if not, it's not that big of a deal for this particular section, but I think you'll be able to follow me even if you've forgotten a lot of your trig. But if I just drop this perpendicular bisector here, right? So we can see the right triangle being formed in our coordinate system. And if we think about our definition of sine of theta, if we think about our definition of cosine of theta, let me write cosine first. So by definition, cosine of theta is simply what? It's the adjacent over the hypotenuse. And the definition of sine is the opposite side divided by the hypotenuse. Now, we've already established that we're dealing with a unit vector, length of 1. So do you understand that this hypotenuse here we know is 1? So I can simply make I can simply insert 1 in for the hypotenuse. All right. Let me just assume that somebody was daydreaming. I want to make sure you understand, if the hypotenuse, the length of the hypotenuse is 1, adjacent divided by 1 is just adjacent. Okay? Opposite divided by 1 is just opposite. Okay, but what is adjacent? What is the opposite? So this would be your adjacent side. This would be your opposite side. Does it now make sense to you that, this point has some x and some y component, right? And in other words, if I'm here and you're here, if you want to tell me how to get to you, you would have to give me, both a longitude and a latitude, right? In order for me to get there. So the opposite and the adjacent, I hope it makes sense that the length of this side, the length of the opposite is just the distance of y, right? Don't you agree with me that y from here to here, right? So opposite is equal to y, and of course the length of this adjacent side is just how far you would travel in the x direction. So all of this baby trigonometry, so that I can simply insert cosine for the u sub 1 component and insert sine for the u sub 2 component. So now vector u is going to be equal to cosine of theta, comma, sine of theta. Almost done. So this is the component form of u, and it's the component form of u if you know the angle, right? Theta. Let's also which is more important to us, let's go ahead and put this in the ij notation. So cosine theta I plus sine theta j. Okay. So let's go ahead and we're going to kind of go back and forth between these, what I've written here. No, I'll tell you what I'll do. Let me go ahead and just take this with me. That way I don't have to come back. Okay, so I'm going to erase this in just a second. Now, it should make sense that we derived this based on the assumption that your vector was a unit vector, right? That it had a length of 1, right? We had to assume that the hypotenuse was equal to 1. Does it now make sense, though, if your vector is not a unit vector? Then if your vector has a length greater than 1, then you're going to have to account for the fact that its magnitude is not equal to 1. Does it make, I hope that makes sense. So does it make sense to you that if this is 1, then of course your vector notation looks exactly like what I have written here. But that again assumes that it's a length of 1. So this, I'm going to put a star here. This is really the formula that you want to keep in your pocket as we proceed. Okay, let's put this to work. Let's try it. So we want to write a vector of a given magnitude and direction. All right. So I'm going to give you a direction. I'm going to give you a magnitude. I want you to write me the vector. Here we go. So it says the vector v has a magnitude of 3 and makes an angle of 30 degrees pi over 6 with the positive x-axis. Let's take some notes. So the magnitude of v is 3, and the theta is 30 degrees pi over 6. Let's keep reading. We're asked, write v, okay, here's that word again, as a linear combination of the unit vectors I and j. And all of that just means is we want vector v, and we want this to be an ij notation. That's all that means. So watch how easy this is. All we have to do is plug 3 in, using our formula above, plug 3 in for the magnitude, and plug pi over 6 in for theta. Do a little bit of arithmetic, and then we're done. Okay, let me write it. So that's going to end up being 3 cosine of pi over 6 in the I direction plus 3 sine of pi over 6 in the j direction. And all right, let's just finish this up. So, well, the cosine of pi over 6, that's just the square root of 3 over 2. And sine of pi over 6 is a half. I've been studying math a long time, but I do tend to forget things like this, or even worse, get them mixed up, and not even know that I'm doing it. But I'm fairly positive that I'm good here. So let's just clean it up. So what is the answer? Here's the answer. 3 square roots of 3 over 2 I plus 3/2 j. All right, so we're all done. That is the answer. Let me tell you what is not the answer. Okay, so, and I'm really, really hoping you're paying attention really quickly. You in this class, you are almost never, ever going to get your calculator and start rounding. Okay. Now you can get your calculator. You can take 3 multiplied by the square root of 3 and then divide it by 2, and you can give me a really good decimal approximation of that, right? You can go out, quite a lot of units, quite a lot of figures. You can give me a really good decimal approximation, but you're still wrong. This is the answer. This is the only answer. And we're not going to round. We're not going to turn pi into 3.14. We're not going to round until someone tells us what margin of error they're willing to accept. I haven't told you that you can round to a certain place value. If this were an application, you might if you're working at a company, and you say you're drilling something or pressing something, they might say as long you need to be within 1/1000th of an inch. Well, that's the margin of error that they're willing to accept. In this, you have no margin of error, right? So we want exact answers unless told otherwise. All right, so we got a couple more problems. I think what I'll do is, I think I'll stop here, come back and do a third part of this video just so we can chop up the material a little bit. It gives me a second to get a drink of coffee. And when we come back, what we're going to do is we're going to take some of this information that we've learned and let's actually see it in some word problems, right? Let's see where would this be useful. I will see you in the next video.